Our next lesson is going to be on thermostoichiometry. And essentially, thermostoichiometry is determining how much energy is released if you're given a certain quantity of some substance. So to start off with, again, we're working with energy. And in the past, we've worked with the value of Q, energy being calculated in the form of calories or joules. And we were saying that if you see a transfer of energy, either energy is being released or it's being absorbed. If energy is being released, it is a process called, it's an exothermic process. If energy is being absorbed, it is an endothermic process. And we can actually show that in numbers. So one of the things that one of the great scientists, Hess, had worked on was he said that we can look at energy as either being released or absorbed by using the value of a delta H. And if you have a negative delta H, some negative number, that means that energy is released, which, as we know, is exothermic. If you have a delta H value that's positive number, that means that energy is absorbed. And we know that is endothermic. So simply by knowing the value of our delta H, we know whether or not energy is released by looking if it has a negative or positive number. So let's take a look, and delta H could look something like this, where you have a number of 68 kilojoules. And because it is a positive number, there's no negative sign, we know that that chemical reaction absorbed energy. It could look like we have a delta H that says that's equal negative 217 kilojoules. And that tells you that in that reaction, 217 kilojoules were released, simply because we see that negative number. So let's take a look at one of those chemical reactions. So here we have a chemical reaction using potassium chlorate, where we have 2 moles of potassium chloride decomposing to 2 moles of potassium chloride and 3 moles of oxygen. So we are making the assumption, and here we have a negative number, that if I have 4.89 grams of potassium chlorate, how much energy is released? Well, right now I know that 2 moles of potassium chlorate will release this much energy, because our energy value is always based on the equation we have here. So this delta H represents anything in this equation. I also know if 2 moles of potassium chloride are produced in this energy, that this whole reaction released 89.4 kilojoules. And that's something that you're going to see why that's so important. Now, we don't have 2 moles. Instead, we have 4.89 grams of potassium chloride. And as you probably are guessing, is, well, we need to figure out how many moles that is so that we can apply this number to it. So it's simply, what we're going to be doing is what we've done often enough before, is we're going to convert those grams into moles. That equals 1 mole. And I simply went into my periodic table. I added the potassiums, 1 chlorine, and 3 oxygens to get the molar mass of this. And then, based on this equation, I know that 2 moles, that's why I'm putting 2 moles, because of that equation, that 2 moles of potassium chlorate are going to decompose and release this much energy. Okay? So I simply put that into my stoichiometry problem. So this is the first new piece of information. I take whatever value I have here, in this case 2 moles, and I take the value of my delta H and place it on top. And I simply do the calculation. And that means that I have a negative 1.78 kilojoules of energy that are released from 4.89 grams of potassium chlorate. That's it. That's all what thermostoichiometry is. So the key to thermostoichiometry is getting this tile. And remember, you get this tile, the moles from the equation, and the calories you get from your delta H. All right, so we're going to have a chance to work through those in the quiz that you'll be taking. So here's another type of example you would use, and I know that it's cut a little bit. So it's saying assume 400.0 kilojoules of energy is released burning butane. How many grams of butane were burned? So here we're doing just the reverse. Here you're given the amount of energy, and you need to figure out how many grams are going to produce that amount of energy. So with that said, you are going to look at this a little bit differently. In this case, our delta H value is given per mole. So it's telling you specifically for 1 mole, this is how much kilojoules are released. So we need to start off with the chemical reaction. And butane, remember MEP-B has CH10. And because this is a combustion reaction, we break it down to reacting with oxygen, and our product is going to be carbon dioxide and water. And this is something that you had learned before, that whenever anything is a combustion reaction, it always reacts with oxygen to produce carbon dioxide and so forth. So, my apologies, this is not balanced. This is what I would get if I were to try to balance this. Let me make this a little bit clearer. Our balanced reaction or equation is, oops, this right here. And simply all I've done is made sure that I have the same number of carbons, hydrogens, and oxygens. I'm going to be not using this equation, but using this equation. Okay, so for that reason, that I know I have 400.0 kilojoules of energy of C4H10 that was, that were released. All right, and I now use this tile here to go, oh, okay, well, if that much was released, I know that it takes 2,882 kilojoules of butane, or better said, 1 mole of butane releases 2,882 kilojoules. I know that because of my value above here. So now I've gotten into moles. All right, the next thing is now I need to convert those moles into grams. And I know that 1 mole of CH4H10 equals 58.12 grams. And for that reason, if I do my calculation, it works out to be 8.06 grams of butane were required to produce 400 kilojoules of energy. Okay? So again, what I did was I took my known variable, which is 400 kilojoules. I then took my tile that I have here, and in this case it tells us that for every 1 mole you have 2,822 kilojoules released. That gets me to moles of butane that I have, and then I simply need to just convert those moles into grams. And that's it.